Good morning, everybody.
Good morning, sir.
Okay, so we already have 35 today. Okay, so let us begin. So that means that some of you were absent in the first class, right?
Yes, sir.
Okay. So let me share my screen. So I think in the last class we were talking about the some of the initial, developments which led to the first successful launch of satellites for communication purpose. And then we were talking about this classification of the satellites. So the basis for classification of satellites could be different. Can everybody see the screen and also hear me?
Yes, sir.
Yes,
So one of the criteria for classification of satellites is the orbital altitude. And on the basis of that, we had in the last class discussed about the low Earth orbiting satellites, which are typically around 800 to 1000 kilometer. And we had also calculated the corresponding orbital period as about 105 minutes, and typically assuming 1000 kilometer orbital altitude, and the orbital velocity was about 7.3 kilometer per second. Now, when we talk about the orbital altitude, you should remember that the distance for calculation of this uh, orbital period as well as orbital velocity, that should be done with reference to the center of the Earth, not the surface of the Earth. So, in addition to this orbital altitude of 1000 kilometer for low Earth orbiting satellites, you have to add to it the radius of Earth, which is roughly around 6400 kilometers. Then we had gone to the other extreme. I say extreme because in case of low Earth orbiting satellites, you will have like a satellite moving from one horizon to the other at a very fast rate, 7.3 kilometer per second. So typically, the orbital the duration of one of those transits is about 7 to 12 minutes. So even at the minimum time interval of 7 minutes, the total spatial distance covered by a low Earth orbiting satellite comes to be about more than 4,000 kilometers during that 7 minute interval. So that is why it is said that for low Earth orbiting satellites, the uh, data that we receive or the signal that we receive, that contains information which is dominated by the spatial change as mentioned over here. If S is supposed to receive signal, then that is essentially a function of X, which is we define the let us define the space by X, and in comparison, the time interval which elapses during one such transit is very small, relatively small, only about 7 minutes compared to 4,000 kilometers. So this is one extreme of uh, satellite dynamics. At the other end, you have a geosynchronous satellite with a typical orbital altitude of 35,800 kilometers. Right at this stage, I am not going into the distinction between geosynchronous and geostationary, but we will do that later. So, geosynchronous satellite is something which is classically and ideally used for the purpose of satellite communication. Although, in the last class, we learned that one of the low Earth orbiting constellations by the name of Iridium, they are also trying to set up a grid of satellite communication satellites using low Earth orbiting technology. That means those satellites will be many in number, and they will be, forming a kind of a mesh, a dense mesh around Earth at low Earth orbiting altitudes. So that was a technological success, but initially the business was not that good. But now they are once again trying to, re-establish themselves. So when I say that geosynchronous or geostationary satellite is classically and ideally most suited for satellite communication, what I mean is that here you have an artificial object in space which is nearly stationary with respect to any point on the surface of the Earth. So, suppose you are having a communication satellite, and if that satellite varies as a function, if the location of that satellite varies as a function of time, okay, then what will happen is that for some hours of the day, that satellite will be at a certain location with respect to the observer. Then after some hours, it may move to another location. So there has to be once again, a change in the direction of the antenna, and in the limiting conditions, it may so happen that that satellite may completely move out of the field of view of the observing antenna. That is the antenna which is receiving signal from that satellite. So when the satellite goes below the horizon, then definitely we know that we cannot receive a direct signal from that kind of a satellite which is below the horizon. Of course, I am stating this qualitatively now. Later on, we will see that there is actually a mathematical relation also, which which we perform before we even try to set up a receiving system for a satellite to check whether that we are actually able to receive the signal from that satellite or not. So that is a geosynchronous or geostation. So that is why a geosynchronous or a geostationary satellite is more suited, because it will have almost no movement with respect to the observer on the surface of the Earth. So that is why we can receive 24 by 7 the signal from that satellite, pointing the antenna towards one fixed direction in space. Now, I'm not saying that a geostationary satellite or a geosynchronous satellite is absolutely fixed. For a geosynchronous satellite, as we will see, that there are certain movements of the satellite, and even for a geostationary satellite, there are some movements. Of course, classically, we define a geostationary satellite By the name of that satellite, it implies that it is stationary with respect to Earth, with respect to any point on the surface of the Earth. So, uh, and the name geosynchronous is more general because it means that uh, how that particular satellite could be stationary with respect to any point. It could be stationary only if it is geosynchronous. That means only if it is moving with the same angular velocity as that of Earth. Only under that condition it can achieve, with some additional conditions, it can achieve that condition that it will be stationary with respect to any point on the surface of the Earth. So India has, capabilities of, and we already have satellites of both these two extreme classes of satellites. One One of the more well-known Indian geostationary or geosynchronous satellite is, of course, the INSAT, the Indian satellite series of satellites. Every one of us is familiar that there have been a number of INSAT satellites being launched by Indian Space Research Organization, and ISRO, with some failures, still had a very good reputation for launching satellites and placing them in orbit, not only for our country, but they have also done it for other countries as well. I mean, satellites of other countries. So the signal that we receive from this kind of a satellite, a geosynchronous satellite, is essentially dominated by the temporal variation of that signal, because that satellite does not suffer any spatial change. So whatever signal is coming is uh, essentially dominated by the variation in time. So can we just quickly, calculate the orbital period and the orbital velocity of a geosynchronous satellite, taking the orbital altitude as something like this, 35,800 kilometers. So please calculate.
So the orbital time period I calculated was 23.96 hours.
And the orbital velocity.
Sir, I'm calculating.
Okay.
Sir, it's about 3.07 kilometers per second.
Anyone else can you confirm this value of orbital velocity? Hassan Sahadi,
Yes, sir, I'm
are you
trying.
okay? And who is Ram or Ram? It's Ram. What's your name? Hello. Someone is having a name of. Okay, so he has now left the meeting. Mayuri Srivastav.
Yes, sir. So I'm doing it.
Okay.
So time period is 23.96 hour.
Yes. And the angular velocity. I mean the orbital velocity.
Sir, I'm calculating.
Okay.
Sir, 3.2 kilometer per second.
3.2 kilometer per second. So Hassan Sahadi, have you completed calculation?
No, sir.
Why? Having problems?
Yes, sir. 3.07 kilometers per second.
Okay. Okay. So what we can understand is that uh, in case of a geostationary or geosynchronous satellite, the orbital velocity is like uh, more than 50% less compared to a low Earth orbiting satellite, which was like 7.3. So here we are having about 3 kilometer per second roughly for a geosynchronous satellite. So that means this once again clears uh, some kind of a misconception that we have, that when we say a geostationary or a geosynchronous satellite, uh, many people, not only students, have this misconception that they do not move. Of course, they move, but they move not with respect to any point, because from any point on the surface of the earth they will remain stationary, but because we ourselves on the surface of the earth are moving, it is moving with the same orbital velocity. So that means just imagine that uh, that is the kind of velocity with which a geostationary or a geosynchronous satellite has to move in order to maintain this condition. That means it should remain stationary, or it should be, its angular velocity should be synchronous with that of Earth. So in between these two extremes of a low Earth orbiting satellite and a geosynchronous or geostationary satellite, we have the third category of satellite, which goes by the name of medium Earth orbiting satellites. That is typically having orbital altitudes of about 20,200 kilometers. Now, unlike the low Earth orbiting and the geosynchronous or geostationary satellites, the medium Earth orbiting constellations, they they were developed much later, 1980 to be precise. The development began sometimes around the late 1960s, 1969, 1970, but gradually it kind of culminated in the development of the global positioning system of GPS, with which many of us are familiar. We use the services of GPS either knowingly or unknowingly. So GPS that was launched, that was designed and launched and operated by the United States Department of Defense, DoD, since 1980. So these GPS satellites or medium Earth orbiting satellites, they are mainly slowly moving. Okay, and because of their orbital altitudes, you can understand that they cannot move very fast at 20,200 kilometer altitude. Neither they are stationary with respect to any point on the surface of the Earth. So these satellites are slowly moving, and the signal that we receive from these satellites are essentially a combination of both space and time variations. Okay, that means it's a combination of both x and t. Now, GPS is not the only medium Earth orbiting constellation, so to say. The Russians have another system, their own system known as GLONASS. Europe is coming up with its own system named after Galileo. China is coming up in a big way with their own constellation named named Beidou 2. Okay, Beidou. And there are some other regional constellations also, but these medium Earth orbiting constellations are not used for satellite communication. That we should have a very clear idea right from the beginning. They are only used or mainly used for satellite navigation purpose, the medium Earth orbiting satellites. So, some of you, can you please calculate what will be the orbital period and orbital velocity of medium Earth orbiting satellites?
So the time period is about 11.99 hours I'm getting.
11.99 hours. See, one thing, is it Chirantan?
Yes, sir.
So when you mention the orbital period, try to mention it in terms of hours and minutes. Okay,
Okay, sir. Okay, sir.
so that should be like what, 11 hours 56 minutes or something.
59 minutes I'm getting.
Okay.
And the orbital velocity is about 3.87 kilometer per second.
3.87. Okay. So what we can understand is that for the medium Earth orbiting satellites, because their orbital altitudes are intermediate between a low Earth orbiting satellite and a geosynchronous satellite, their orbital velocities, they actually, that creates a bit of a problem, because the spatial variation of the signal, which is contained in the signal, that contaminates the temporal variation and vice versa. That means, like in the case of a low Earth orbiting satellite, we say that whatever variations in the signal we observe is mainly due to the space change. And in case of a geosynchronous, we could say that it's mainly due to the variation with time. In case of a medium Earth orbiting satellite, we cannot say that for sure, that this is mainly due to spatial variation or mainly due to temporal variation. So there has to be some kind of, uh, you know, deep trending. That means trying to eliminate one effect from the other before we could say with confidence that the signal variations are more likely due to space or more likely due to time. So, these medium Earth orbiting constellations, which are used for global positioning, which are used for satellite navigation, basically they have a history of being evolved out of military operations, both GPS by the US and GLONASS by the Russians. They were developed as part of the Star Wars program that happened a long time back before any of you were born, around the 1980s, and uh, that continued till the then USSR, that was finally, kind of disintegrated around 1989-90, that period. So GPS and GLONASS are both products of some kind of a military operation, and later on their signals were made available to the civilians, starting from around 1994. And our department, that has played a very important role in India in this regard, because we were one of the first universities in India to start operation of this GPS signals in India. That was way back in 1994. At that time, India only had two GPS receivers. One was in our department, and the other one was at the National Physical Laboratory in New Delhi. At that time, ISRO or any of the other institutes were not even aware of what GPS stands for. So, as I was mentioning, that in many of the books you will find that geostationary and geosynchronous, they are mentioned in a way which makes you think that they are one and the same. But geostationary and geosynchronous are not exactly the same. There are points of differences between the two. Like, uh, as you can recall, that it is Kepler's third law which sets the ball rolling for us in terms of calculation of the orbital period and the corresponding orbital velocity of a satellite. So they were, derived for a for a special case of circular orbits. But later on, that became extended to the more general case of an elliptical orbit. Okay, so the conditions that has to be satisfied for a satellite to be perfectly geostationary is that uh, number one, the orbit of the satellite must be exactly circular. That means the orbital eccentricity should be zero. Secondly, it must be at the correct altitude. That means that 35,780 kilometer altitude. And thirdly, it must be in the equatorial plane. That means it must have orbital inclination of zero. Now, this orbital inclination is actually the angle measured between the equatorial plane and the orbital plane of the satellite, right? So If a satellite is in the equatorial plane, that means a plane which passes through the Earth's geographic equator, then definitely the angle between the equatorial plane and the orbital plane is zero. So that is one of the important criteria out of three, which makes the orbit of a satellite perfectly geostationary. That means geosynchronous orbits can have orbital inclination non-zero value. That means their orbital planes can make an angle with the Earth's equatorial plane, and their orbits could also be non-circular. That means they can have a non-zero value of the orbital eccentricity. So if these two conditions are there, if they exist, then the satellite will be in a geosynchronous orbit. So that means a geosynchronous orbit or a geosynchronous satellite is a kind of a special case of a geostationary satellite, right? That means when the orbital inclination becomes zero, that means the satellite is in the equatorial plane, and or when the orbital eccentricity is zero, that means the satellite orbit is exactly circular. So under that condition, a geosynchronous satellite becomes a geostationary satellite. So all geostationary satellites, they are geosynchronous, because geosynchronous is the general form of these satellites, but all geosynchronous satellites are not geostationary. But that means the reverse condition is not true. So what we can understand from here is that uh, geostationary satellites are a special category of geosynchronous satellites only when they satisfy these conditions, that their orbital inclination should be zero and their orbital eccentricity should be zero. And of course, they must be at the correct altitude. So when these conditions are satisfied, only then does a satellite, the orbit of a satellite becomes perfectly geostationary. So a very important, takeaway from this uh, information is that uh, a geostationary satellite will always lie over Earth's equatorial plane. So now, if I ask you this question that uh, from India, from Calcutta, say, we want to receive signals from a geostationary satellite. So in which direction shall we point our antenna? From Kolkata, we would like to receive signal from a geostationary satellite. So in which direction, north, south, east or west, should we point our
Sir,
antenna?
in southward direction.
Why?
Sir, because the equator is in south and geostationary satellites are always situated at equatorial plane.
Why do you say that the equator is south of us?
Because we are in northern hemisphere.
So what is the, and do you know the latitude of Kolkata?
Yes, sir. It is about, I'm not 100% sure, but about 20 degree north. Because
22 and a half. 22 and a
maybe yes,
half degrees north. And
yes,
the
sir.
equator, what is the geographic latitude of equator?
That's 0 degree.
0 degree. So
Yes.
that means from 22 and a half degrees north, you have to point your antenna towards 0 degree north. So that is south. So that means from any country in the northern hemisphere, whenever they want to receive signals from a geostationary satellite, they have to point their antenna, or even geosynchronous, they have to point their antenna towards the south. Okay. Now, I think that none of you has been to our department so far, physically to our department. Has any one of you visited our department so far?
Sir, I have visited, but for library purposes.
Yeah. So, what's your name?
Satchirantan.
Okay, Chirantan. So, at least for those, even if you have not visited, but if you are from the Kolkata region, around Kolkata, you can understand a little bit of the, the geography. So, suppose from the roof of our department, we want to set up a geostationary satellite receiving system. So, we have to have the antenna on the rooftop, right? We cannot have an antenna within the room itself. It has to be out in the sky. So, looking north from our department, we are basically looking towards, say, Shambhajar. Okay.
Yes.
And looking south, it's like, say, Shialda. And on the east, you have, say, Salt Lake Stadium. And on the west, you have the Howrah Bridge. I mean, these are landmarks, which are with which students from around the Kolkata region are more familiar. It is easier for them to identify this. So that means, going by what we have just learned, that from Kolkata, or for that matter from anywhere in India, when we want to establish a satellite signal receiving system, a geostationary satellite signal receiving system, the antenna has to be pointed towards the south. So, in our case, from our department, it means essentially that the antenna should be, kind of pointed in any direction over the entire southern quadrants. The southern quadrants meaning starting from maybe the southeast, almost due south is Shialda. So southeast is something like, say, Salt Lake. Almost south is, due south is like Shialda. And moving on to southwest, like Borobajar, say, for example. So over this entire portion of the sky, combining these two quadrants, the southeast and the southwest, the satellite could be located anywhere. So, even for those of you who are not familiar with these landmarks in Kolkata, if you are using some kind of a direct to home, a DTH service, say any of the operators, if you just go up to your roof and take a look at the antenna which their people have set up, a small antenna, maybe 3 feet in diameter or so, then you will also find that that antenna is pointing towards the south, maybe
Yes,
either southeast or southwest. That is because of the fact that these DTH services are also supposed to be operational 24/7. That means they have to track the signal from geostationary satellites. Because otherwise it may so happen that you will receive the service if these satellites are moving with respect to time, then it may so happen that for some hours of the day, that when that satellite is visible to your antenna, radio visible to your antenna, you will be receiving the signals, and when that satellite moves away, you won't. So that kind of a situation cannot be, cannot be used. So for that matter, for these DTH services also, some kind of a geostationary satellite has to be tracked by the receiving antenna, And that is why the antenna, which is kind of installed on the roof of your building, that also has to be pointing towards the southeast or the southwest. You may just check that at any time. Now, this is just one example of an Indian constellation that we have more recently, which uses a combination of both geostationary as well as geosynchronous satellites. Okay, so this is the IRNSS. The full form is Indian Regional Navigation Satellite System. This is not used for communication. Mark my words. Okay, but I wanted to show you this figure in order to make you understand that when you have a geostationary satellite like this one, IRNSS 1F, or that one, IRNSS 1C, or the next one, IRNSS 1G. These three satellites are all over the geographic equator, which is marked by this green dashed lines. So these are the three satellites which are over the equator. So because classically or theoretically they are all stationary with respect to any point on the surface of the earth. So of course you can understand that from this global map that this is India. So the geographic equator is south of us. So these are the locations of the three geostationary satellites. And there are some geosynchronous satellites also in this constellation. And these geosynchronous satellites, because their orbital inclination is non-zero, and because their orbital eccentricity is also non-zero, so they describe some kind of they move, and their tracks on the surface of the earth describe some kind of a figure of 8. Okay, as you can see, this is a figure of 8 that they are describing, covering the two hemispheres. Okay, so this IRNSS constellation uses some geostationary as well as some geosynchronous satellites. Now, naturally, as we go on further in this course, we will discuss that why and under what conditions geosynchronous satellites are necessary for satellite communication. Today, I think I will stop here because I have another meeting at 10 o'clock. And so I will continue with this in the next class, which I think is Monday. Okay. Have you received the routine, your routine?
Yes, sir.
Yes, sir.
Okay, so just a minute. Let me have your attendance now. Okay, so sequentially, please tell me your roll numbers. 301, I think, right?
Present, sir. Devjit Ghosh, 301.
Okay. Then, next.
302 sir, Parmita Banerjee.
Thank you. Next.
Shubhodip Mukherjee, 303.
Okay. Next.
Sir, 305, Moshumi Shao.
304. So nobody is 304, right?
Yes, sir. There is no
No,
one.
sir.
Okay.
Sir, 306, Monisha De.
Okay.
স্যার 308 সপ্তর্ষি গাঙ্গুলি।
Okay. Next.
Sir, 309, Shoumi Mondo.
Okay.
311.
Yes. Your name?
So Sheikh Mohammad Safiq Anwar.
Okay. Next. After 311,
Sir, 314 Romana Mujumdar.
Sir, 313 Srija Chakraborty.
okay,
Sir, 315 Moushumi
next,
Mondal.
okay, next, okay, next,
At 318, Somajit Vasak.
okay, then
Sir, 320 Debangana Boshak.
Sir, 321 Ognisha Bhomik.
just 1 minute, just one. Devangana, what was
321
it? No, Devangana, what was your roll number?
320.
320. Okay. And 321 is Ognisha.
Ognisha Bhomik. Yes, sir.
Okay. Then,
Sir, 322.
yes.
Sir,
Okay.
323 Subhashish Ghosh.
Okay.
401 Shalini Roy.
Okay.
Sir, 405.
Okay.
Sir, 407.
Okay.
408 Shohampal.
Okay.
411 Shagnik Nayak.
Yes. Then,
Sir, 420 Chirantan Ganguly.
okay.
421 Aniruddha Mandal.
Okay.
Sir, 422 Amit Rakhor Sannal.
Okay.
423 Dipro Chakraborty.
Okay.
424 Soham Kundu.
Okay.
Sir, 430 Pothikrit Gupta.
Okay.
431 Mayuri Srivastav.
Okay.
432 Mrityunjay Kumar.
Okay.
433 Pratyush Kant.
Okay. Next.
435 Ram Pravesh Kumar Gupta.
435.
Yes, sir.
Okay. Then,
Sir, 438.
Sir, 437 Sriyastri Roy.
437. Okay. Then,
Sir, 438 Prasant Kumar.
okay.
Sir, 439 Ritu Majumdar.
Okay.
440 Shoham Adhikari.
Okay.
441 Suprabhat Bhattacharya.
Okay. Anyone else?
Sir, Sharon Dotto.
তোমার রোল নাম্বার পাওনি তাই তো?
No, sir.
Ravi Kumar Thakur,
Okay.
sir.
Yes, your roll number?
Not provided, sir.
Okay. Anyone else? Okay.
No, sir.
Okay, so thank you, and so the next class will be on Monday. Okay.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.